So today we will finish our curve fitting and hopefully start with differential equations. So let's just quickly review. First, the least squares regression for a linear type of model. So in general, if I have a bunch of data, I want to actually describe it in form of a functional relationship. And in that process, I have to kind of look at the data and decide what would be a good functional relationship that I'd like to model this with. The simplest one we can ever think about is the linear one. Okay? It doesn't always work, but that's something that we can assume. And that's what I refer to as a model. So you have to decide what your model looks like. Okay? And then you have data, and you have the model. And the way we actually, when you have a number of points, okay, and they have, for instance, x and y variables, so xi, yi is my array of points that I have. So then the way I evaluate the error that I'm making with the model is I take that yi, which is the measured value, which is my input data, and I look at what would models say for that x value, xi. And I look at the difference between the two, and I square it. And when I sum up all of those differences, that is sort of this SR, we call it least square residuals. And the way we go about finding this model, or parameters in the model, typically I have 2 or 3 or more parameters that define my model that are built in here, is that I'm going to take partial derivatives of this SR and set them all to 0, and that will guarantee that I have a minimum that I'm trying to achieve for that SR. And since SR is positive, it's going to have a minimum. It's not necessarily going to have a maximum. And when we do that for a straight line model, so if my bi model is just a straight line with 2 parameters, I will get a 2 by 2 linear system that I can solve. And my A0 and A1 are given with these expressions here in terms of the data that comes in. Now, I can imagine that if I have a nonlinear model, okay, something involving sines or cosines or exponentials or you name it, okay, then I will start getting into trouble in terms of computing these partial derivatives. So when I actually go through the process and set those partial derivatives to 0, I might get a set of nonlinear equations, not a set of linear equations, because my model is complex. So we often want to avoid that. So you can actually see that in the case where we were deriving this. Okay? So imagine if this was, instead of A0 plus A1 xi, you actually had A0 exponential of xi or something of that sort. When you would take something that has actually A1 under that exponential, okay, then basically when taking partial derivative with respect to A1, you would get some sort of exponential function and complications here. And that will prevent you from getting a linear system in A0 and A1. It would be a nonlinear system in A0 and A1. And you will see how much fun that can be in your computational project. Okay? So we want to avoid that situation of creating a system of nonlinear equations. It turns out that we actually can, and we went through that exercise last time. It's possible to linearize some of the nonlinear equations. For instance, if I take natural log or any log, a natural log in this, we had this power law. And if I take any logarithm, natural or log 10 or whatever it is, of both of these sides of this equation, I'm going to get that log y is log of this first parameter plus b2 times log of the second parameter. So essentially, log of x and log of y are assumed to be linearly related, because I can take this as a new variable uppercase x and new variable uppercase y, okay? And this uppercase y and x are related a linear way. This is my new intercept, and this is my new slope. I can do that with anything. So let's actually just do an example. Assume that you're relating your data as y equals to 1 over 1 over m, where n is some parameter plus b. Can you transform this so it's a linear relationship of some variables that depend on x and y, and what would those variables be? Take a piece of paper. So y is equal to 1 over mx plus b. Which two variables or combinations of these things are linearly related? So I have some data xi, yi. So x and y are my initial input data. But all you need to is transform this equation. What's the first thing you'd like to do with that? Yeah, rearrange. So what would you rearrange? What is mx plus b equal to? Do I see a linear relationship in there somewhere? One over y is mx plus b. Who is linearly related in this? Can I define some new variables that are linearly related here? Can I? Well, one remains the same, x, and the other one is 1 over y. So if I define this as y, and this is uppercase x, uppercase y is mx plus b. So all I'm going to pass to my linear regression function that I programmed is my original x data and 1 over y data, and I'm done. Okay? This is what we were doing with logs last time because we were trying to fit in a power law. So often you can actually, that doesn't mean that every relationship can be manipulated, but a lot of them can, and then all you're doing is you're using your linear regression code. Questions? So there's actually an entire list, and even this one is not necessarily super straightforward, but you could actually modify this to have that 1 over y is b3 over a3, 1 over x plus 1 over a3, and again, this variable and this variable, which are transformations of my original variables x and y, are linearly related. Okay. All right, so there's like an entire list of suggested values, and this is the one that I just did for you. Okay. And this was the exercise we completed with the power law. Okay. So we actually saw that in the case of the data that I gave you, is there was one outlier, but give or take, that outlier, this power law, this red line, is fitting the data rather well, except for this outlier point right here. And it fits much better. The way we measure it is so-called R squared that I can compute. R square fit here for the line is 0.75, which is not very good. Below 0.8 is typically not a very good fit. And something closer to 0.9 is always better. And 0.9 fit is this power law fit, and that's pretty good. All right. And then if I need to use this data, so the reason why I'm doing this is that in my well, I might have a complex relationship, say, between permeability and porosity. Just having all of the data is typically messy. It doesn't behave well. When I fit it with a function, then I could just use that function in whatever models that I'm doing for this data. So you might have a reservoir. That reservoir will have all of the individual blocks that are, for instance, different sandstone blocks. Each of them is characterized with porosity, so you would really like to have a functional relationship that says, oh, your permeability in this block is really some coefficient times porosity squared divided by whatever, some function of porosity. Right? And when you do that, it's really then to define permeabilities. If you can define permeabilities easily, you can solve Darcy's law on this entire reservoir relatively easily. So we like these relationships or functional relationships, and even though it's not exact relationship, it might be close enough for the predictions that I need to. Okay. So this is where you will often do curve fitting. All right. Now, not linear regression is not the only type. Let's say that we are trying to fit a polynomial. So this is just an example that essentially reinforces what we've done so far. So I'm just going to walk through it. How would you do it? Again, let's say that like I have data like this. So it kind of looks like a parabola, right? I look at it. So my guess is that this fit parabola is parameterized with 3 parameters, A0, A1, A2. Okay. This fit looks like it should be a good one. So this is going to be my model. And then I have data is my model plus some error. And now my residual looks at every point is the data, yi, minus the model computed for this xi. Okay? And when I take those differences and I square them, I'm going to get my sum of the squared residuals. And that's what I'm trying to minimize. So what is my procedure to find the minimum of this function? I can think about this as a function of A0, A1, and A2. What's the next step? Differentiate it with respect to A0, A1, A2, because those are the things I'm trying to find. Everything else, my data, xi, yi, I have. So partial derivative of this with respect to A0 would be basically 2 times sum, okay? And then times minus 1. This is basically a chain rule here. Okay? Partial derivative with respect to A1 would be 2 times sum of these without the square times minus xi. Okay? So there would be a sum of these times minus xi. And the last one would actually have minus xi squared. So if I actually do that, so that's just a procedure. So basically, I would have this. This is this 2 times minus 1. That's equal to 0. Okay. My next derivative is actually equal to this with respect to a1. And the third one actually has this xi1 square. And when I clean this up, okay, ultimately, yes, I have these sums of xi's and yi's and xi squares and xi cubes even, or 4 to the 4th, okay? But when I clean it up, it's ultimately a linear system in terms of A0, A1, A2. So when I clean it up, this is what I actually get. So this is really just a 3x3 system that I solve. And it's relatively easy to see how to program this, just like we had linear regression. This could be called parabolic regression, okay? Or polynomial regression. And basically, with incoming data, vectors xi and yi, I compute all of these sums. And once I compute them, this 3x3 system is relatively easy to form, and I can just employ MATLAB or my Gaussian elimination on a 3x3 system. It's not a big deal. Okay, it's not going to be all that much error. Okay, so I can use Gaussian elimination that I already have programmed, and I'm done. Okay,
So essentially, I can find A0, A1, and A2. So this process is kind of always the same. So this is an example fit to these points. Again, I'm not perfectly going through the points, but I'm minimizing the sum of these residuals squared. And that's the process. So one could use polynomial regression. I could have different types of data, so it doesn't mean that I have to have just X and Y. I can actually have multi-dimensional data sets. So I might have points x1, x2, and y. Okay? So I can have something that depends on two variables. So my data comes in as x1, x2, y triplets. Okay? Again, the way I would do this is that I assume a functional relationship between y and all other. So let's say that we had a linear regression for multiple points, like triplets like this. Then I would assume that I have my model as y is equal to a0 plus a1, this x1 plus a2, x2. So these are my two variables that y depends on. And I'm basically looking for a plane, right, that describes this cloud of data the best in 3D. And again, all I'm really looking for is these parameters a0, a1, a2. So I'm going to set my residuals as the value yi minus my model, depending on the other two data points that I have in each triplet, squared. And I'm going to take partial derivatives and basically, whoops, derive the equations. And what happened right here? I don't know. So in this procedure, again, this will actually give me a set of linear equations in A0, A1, A2. The rest are sums that depend on data. So it's just really about algebra.
How would we calculate like the R squared?
So R squared would have a slightly different definition. So that I can give you the formula for that.
And in the homework, we're supposed to calculate it for a parabolic curve. I'm not sure if you have.
For parabolic curve, it's the same as having data. This is different. So for a parabolic curve, you would solve it the same way as you would for the other.
I was just wondering because we have A2 additionally compared to just like a linear graph.
There is no A's here, just the data. So the definition remains the same. So this residual is not really depending, it's just depending on it. So in that sense, it's not a big deal. You could also always use this as one error estimate as well. So we didn't really work with this one, but you can compute your SR for any model you have, and you can take that as a value. Okay? And that's essentially it. Basically, regardless of the model, what you would form is you would form this sum of residuals squared, okay? And we're looking for the minimum of that. So the procedure says set the partial derivatives to 0, and that will actually give you a set of equations in the parameters you're looking for, okay? And for straight line, we can actually have a regular ready-to-go formula. For anything that has more than 2 parameters, it's hard to come up with a ready-to-go because you're then solving at least 3x3 system. But we know how to solve linear systems. That's one of the key things that we are learning here. So basically, you can figure out how to do this. And there are different, basically, based on the model that you're employing or assuming, you have different types of regression. It could be linear if the model is linear. I could linearize something that is nonlinear, such as power law. I could do polynomial fit, multiple linear, or some other nonlinear that is basically different from linearizing, but that kind of involves possibly a set of nonlinear equations. So it's typically avoided. So these first 4 are the preferred modes. Okay, and if you need to read more on either polynomial and multiple linear regression, you can refer to 15.1 and 15.2. It should be easy to follow because essentially the procedure of setting things up is the same. And as I mentioned, in terms of reading, there is chapter 14 basically covers linear regression in details. This concludes our curve fitting. Do we have questions? Yes.
So for the error part, so for the coefficient of determination R squared, the closer it is to 1, the better.
Yes.
The bit is wrong.
Yes.
What about for the XY axis? Is it smaller than 1?
Yes. But that smaller slightly depends on the functional relationship in the data itself. So it's a little more, when comparing how small something is, then it's a little harder to judge. But yes, the smaller the better.
Which is why R2 is kind of commonly used because it's across the models, regardless of the model. All right, we're going to start the new lecture, and I have uploaded a PDF, or you can just follow the lecture right now without the PDF. Okay. So we're going to switch to your favorite topic, which is ordinary differential equations, right? What's your favorite course? Maybe not. Well, good news, good news is that you will not have to know how to analytically solve anything. Maybe yeah, that was so boring. So, that was a good yawn. So, ordinary differential equations, yawn. Basically you will not need to know how to analytically solve. You're basically taking a course that is teaching you how to solve things analytically and get a closed formula solution. But that's about 1 to maybe 5% of problems that you need to solve in real life are actually solvable like that. For a lot of, or vast majority of problems out there, we don't have a solution that is ready to go as a formula. So in those cases, we actually have to employ numerical methods. And just like we did actually in the example, so one of the examples, the temperature solution that ultimately came down to solving a system. In that particular case, what we did is like you discretize the space, and what you're actually looking for is for the value of the function in these discrete points in space, rather than the functional form of the solution. So any kind of numerical solution to a differential equation will really just give me value of my function I'm looking for. Let's say that I'm looking for a function y. I'm going to get value of that function at discrete points. If I'm on a line, it's going to be one-dimensional problem, so it's going to be my pairs xi and yi. If I'm in 2 dimensions, so I'm on a plane, I'm going to have values for every pair xy in my plane. I'm going to discretize that plane in a bunch of boxes, and in the middle of each box, I'm going to have a solution. And in 3 dimensions, I might actually discretize my reservoir in 3D. Then I'm going to have actual boxes, 3D boxes, and I'm going to solve for, say, pressure at the middle of each box. And that's something that you will be doing a lot in reservoir simulation later. But here we will just exemplify how to solve ordinary differential equation. So we will have a simple case. So I have completed curve fitting. We will skip interpolation. And I will, at the very end, get back to integration if going through a differential equation goes as planned. So there might be literally 1 lecture on integration as just a quick introduction. Bless you. All right. So here's one example where I might get an equation that I don't know how to solve analytically. So let's say that I'm looking for a water height. Okay. I have a tank. This tank is discharging through a hole, and it's filling up through a different type of pipe. Okay. And I have certain area of the tank and this height. Now, discharge here on this end, and how fast it goes, kind of depends on the pressure here and how much head I have. Okay. So basically, because of that, I'm kind of dependent on H to know how fast I will go through here. And whatever is coming in is some sort of, I might actually have a functional relationship that describes of how fast I'm flowing in. Okay. So how I'm flowing in, of course, depends how high I am. So there's this convoluted relationship between how much height, and of course my height depends on the difference between whatever comes in and whatever comes out. Okay. So I'm going to get an equation that is not necessarily simple to solve. So basically my water flow, let's say that it's defined through a cosine, and I have some parameters that I know, K1, K2, and C, that tells me how does this change of mass coming in time. So I just assume that is given. Okay. And then my rate of flowing out depends on the height, and that can be worked out to be density of water in the tank times what is the area here of the pipe, or hole, rather, and square root of 2gh. Yeah. So I know that the change of mass in this tank is simply difference between the two. So whatever is coming in minus whatever is coming out, that's essentially what the change of mass in the tank is. And then the only thing that I have to actually figure out is that mass of this water in the tank is what? It's the volume times rho, right? That is simple. Okay? And my volume is the volume of a cylinder. Okay, so it's this height times area of the tank. So basically, when I incorporate that, what's changing in tank area, and rho are not changing in time. What's changing is this height. So dH dt is whatever is coming in minus whatever is coming out. So this entire expression is a function of both time and height. So I have the dH dt is a function of both h and t. So integrating that is not necessary. Now, I could actually probably, what would you do here if you were solving it analytically? Maybe separation of variables. Put everything to deal with h on one side and everything to deal with t on the other and try to integrate. That's an option. I didn't try it. I don't want to. I have numerical tools. Okay. So I could determine this tank height if I'm pretty good at ODEs. I don't know. I didn't try to. But we could also do it numerically. So just before we proceed to how to find things numerically, let's just throw in a couple of definitions and see what we will actually work with in this introduction. We will actually work with time-dependent problems, such as this example that I just gave. Okay? And they're going to be initial value problems. So I'm going to give myself an initial value of h at time t is equal to 0. Okay? And from then on, I would like to see what happens. Okay? So those are so-called initial value problems. There are boundary value problems, and that's the one with the temperature that I exemplified in linear systems. And those are typically solved just like we did with linear systems, yes? They're just given numbers. There's some coefficients. So I have them as a model. I have K1, K2, and C. They're not unknown. The only unknown is T in it. So, second thing that I actually have to figure out is what is the order of my differential equation. And I have first order equation. dy dx is some function of x and y. That is a first order equation because I only have a first order derivative involved. If I had second order derivative, this is one example. We will learn how to do this. This can actually be formulated as a system of ordinary differential equations. Does anybody see how? So I can actually try to pose this problem as a system of ordinary differential equations, basically for two different functions.
You just take something like x1 equals your y and your x1 prime.
So I could look for dy dx and d squared dy, d squared y dx squared. And then my missing equation would be, so my first problem is that, let's say, instead of y, I'm going to call it f is equal to dy dx. Okay? And df dx is then simply correct? And that, according to this, is 4. So my first equation is just simply setting, okay, I'm going to define myself a new function, which is the derivative of y. And the second derivative of that function is 4, according to this. So that is my system of equations, and I'm solving for two functions. One of them is the y, and one of them is f. We're going to get to that at the very end of the example. Okay. And finally, I have partial differential equations, which we are not going to deal with here at all. And one example would be, this is Laplacian of pressure is equal to 0. Laplacian of pressure, Laplacian of a lot of things can be 0. Okay? So that is basically generalization of this equation, just in 2 dimensions. So it shows up a whole lot in any kind of problems. Okay? But yes, I can actually, Laplacian of pressure is often 0, so you can solve for pressure that way in certain set of circumstances in fluid flow. All right. So as I mentioned, we're going to deal with initial value problems. So they're going to have the form dy dx is f of xy, or dy dt is f of ty. However you want to call your variables, doesn't really matter. So let's assume that we call them this way. So typically what we have is that we're going to have certain initial value. So I'm going to have a value given at a point. And then I want to, basically from then on, I want to solve for the values of y at a certain interval involving that initial point. So what I'm going to do really is I'm going to subdivide this interval, and I'm going to take a small width h, and I'm going to kind of march through the interval and compute these other values. So first and simplest way to do that, just heuristically, is okay, I have this new value at the new point that is h away from my old point. I'm just going to give myself that new value as some old value that I had previously. It could be the one that I'm just starting from. And plus some slope times h. So this is the simplest thing I can come up with. And basically you just go step by step and trace your yi's. So I can see this as a nice little iteration. Okay? I can already formulate my MATLAB code, right? That will actually do this. Nice little for loop, okay, or while loop, whichever one you prefer. I just have to figure out what this phi is in order to actually do that. Well, the simplest one would be, so let's say that this is actually the function that I'm trying to find out. Okay, I don't know it, but this is the function that is solving my problem. Now, if I'm at this point, okay, that's my starting point where I actually know the precise solution. Then, taking this at next point, this is my step size h, and now I really want to find this value, that's my function at xi plus 1, which is h away. Now, the simplest thing I can ever do is just draw a derivative here in the slope, right? So the slope of this is derivative of the function at this point, correct? Do we agree? Okay. So basically my simplest approximation would be to say, okay, well, my new value is the value yi, which is this value here, this height, okay, plus slope times h, this is h, okay, and this slope is actually given as dy dx, correct? Evaluated at this point. Are we following? So, but I know what dy dx is. According to this differential equation, is this function f of xy. Cool, so all I'm going to put instead of the slope is f of xi yi, because that's my slope evaluated at point xi here. So essentially, my slope is dy dx evaluated at this point xi. Okay? So this is where my slope is taking me to some predicted value. My true value is not that. This is the first approximation to it. Okay? But I'm hopefully relatively close. Okay? And I'm always, I know in numerical methods that I'm always going to have some error. I just have to figure out how much. Okay? Euler came up with this, okay? German mathematician Leonhard Euler. It's relatively simple, but when you're first, then you get a whole branch of mathematics named after you. So essentially, yi plus 1 is this yi plus f of xi yi h. If I give you function, or I give you a problem, dy dx is f of xi, f of xy, and I give you a starting point, for instance, y of 0 is equal to 1. Do you know how to program an iteration that solves for all of the y's on some interval? It's a simple code, actually. It has really one line of computation. Okay? So let's actually, I'm going to get back to error analysis after. Let's do that. So I want to basically consider this equation, dy dx, as this function. And actually, I'm going to give you analytical solution so you can check your problem. It's a simple integration here because I don't really depend on y here. But I know that y of 0 is equal to 1. And I would like to solve this with Euler's method on interval 0 to 4. And my step size h should be 0.5. So first thing that I'd like you to do is to just do it by hand before you start programming, and then we'll program. So if dy dx is equal to this, and my Euler's method is given. So my f of xy is defined as this, which is really f of x in this case. But that's so that I can easily integrate and find an analytical solution, so I can check on myself. So let's see how Euler's method works. Oops. Lab is apparently going to take a moment.
So if my x1 is 0 and y1 is 1, so that's the starting point, initial value. How do I get to, what is my x2 according to this problem? It's step h away from my starting point, right? And h is 0.5. So if my x1 here,
if this is 0, then my x2 is x1 plus h, so that's 0.5 in this particular case, right? So according to Euler's method, what is my y2? It's y1 plus this function evaluated at x1, y1, right, times h. Yes? So if I write that, if I write that down, my y2 is y1 plus f of x1, y1, and excuse me for not doing subscripts, times h. Which in this particular case is y1 is 1, right? This is f of 0, 1, this f. So it's really, this is really a function of x, so it's really 8.5, because for 0 it's easy to compute. So it's 8.5 times h, which is 0.5. Yes? So what do I get here as Euler's method? I'm just gonna do this lazy way, so I'm just gonna say 1 plus 8.5 times, that's 5.25, okay? Now, what is my analytical value? There's actually here a polynomial, okay? So I'm just gonna say x is 0.5, and I'm gonna compute what is my y. It's minus 0.5 times x to the 4 plus 4 times x to the 3 minus 10 times x squared plus 8.5 times x plus 1. So I'm quite a bit away if I typed in everything correctly. 4, I think I did. So what is my relative error here? How do I compute relative error between my estimated value, 5.25, and my actual true value, which is 3.21 or something? How do I compute relative error?
3.21 minus 5.25 over 3.21.
Right. So basically, estimate minus true, absolute value, divided by true, right? So basically, I'm going to say, so error is 5.25 minus, I call that y, whoops, divided absolute, divided by absolute of y, and that is 63%, so I'm quite a bit off. Okay. Do we see the procedure? So the way I would now go and continue on this entire interval, okay, is that I would now step
by this h of 0.5 and compute the next value. So my y3 is y2 plus f of x2 y2 times h. Keep going until you hit 4. Yes? And that's essentially it. So that's a simple for loop that we're going to program next time. And then we will see, so what is my expectation as I get this step h of 0.5 is kind of big, right? So I would assume that if I get a smaller h, I'm going to get closer to the actual value. And I can just show you what that will look like before the class ends, and then we will going to get there programming next time. So essentially, if I actually now, so this is my 0.5, okay, so I'm quite a bit away. This is my analytical solution, okay? So this is quite a bit of distance away. But if I go to 0.1, I'm going to get closer. And as I reduce h, I'm going to be closer to the actual analytical solution. Okay? And for systems or for methods that do this, we can say that they converge. All right. We will get to programming on Friday.